So today we're going to talk about data-efficient reinforcement learning. So let me start by saying that just last week I was with a potential client, and they said, why should smarter people that implement reinforcement learning in our product? And I said, I believe in reinforcement learning so much that I even use it in my personal life. And they were like, oh yeah? And I said, yeah, just the other day, my wife said, I need to learn how to do dishes. And I was like, great, I could apply reinforcement learning to this. Now, my wife was surprised at my enthusiasm, but she sees the opportunity and said, well, what do you need? And I said, after thinking about it, I could do with 1 million plates and 100 sinks, and I could start training. Needless to say, we bought a dishwasher. So what we're going to talk about today is reinforcement learning. Now, reinforcement learning's had some really significant breakthroughs. We've obviously seen them play Atari games and that kind of thing. Last year, AlphaZero came out with a single stack and world champions in chess, shogi, and Go. We also saw now recently multiplayer games getting tackled with reinforcement learning, but all of these things have something in common. They're all kind of playing in the mind of the computer. They're not really interacting with the real world. And that's what we want to talk about today, is how do we get these things to interact with the real world? So, just so we're all on the same page, let me kind of give you my definition of reinforcement learning. And this particular thing is we have an agent. And the agent has a way of being able to control its environment, act on its environment by basically various controls or levers or that kind of thing. The environment obviously changes, and the state information about the environment is fed back to the agent, and there's also a reward function that may come from the environment, it may come externally, it may be calculated externally on the environment, it can be some combination of the two. So a lot of advantages for reinforcement learning. The first one is we're moving away from just, say, classify images or recognize faces or even just do a translation. We're now starting to get the technology where we control the environment, and that's very exciting, and that's now taking AI to a whole new level, when you can actually get it to control and manipulate its own environment. Another thing for anyone that's actually done AI in the real world, is you spend enormous amounts of time trying to tag and clean up and collect data. So if you're trying to get these systems to work, you have to do a lot of work with data. And reinforcement learning offers the promise of not having to tag all that data. Where in some ways it's saying, here's the data agent, you figure out how you're going to use it to maximize your reward. And then another advantage of it is that the reward itself can be sparse. It can be sort of lumpy. You don't need to keep giving it constant reinsurance. Like you don't say, hey Johnny, you did a little bit better today at school, or Johnny, you did a little bit worse. It can wander along for a bit and you say you're dead. Or you can wander along for a bit and say, oh, you got a gold coin. And it can figure out how to project into the future and actually make good decisions and maximize its reward. So for all of its strengths, it's got some pretty significant weaknesses currently. The first one is it's very simple and efficient. So if you look at when it's playing a video game, it might need 10 million, even 100 million frames before it actually gets decent at playing a game. And that's going to be a lot of data to try and collect in the real world if you're doing something with robotics. Another problem is if you say look at the AlphaZero stack that they use for their gameplay, it's enormous. It's not going to fit onto edge devices. So if you're trying to make something you're deploying into the real world, say a small robot or a consumer device or even a medical device, those networks are far too large to actually fit into reasonably priced hardware. Now, in the olden days, we could say no problem, 10 years' time, Moore's Law takes care of it, but Moore's Law is kind of sputtering out. So we need to start thinking about how do we make our policies and networks more efficient. And then the final one you don't hear so much about, but reinforcement learning has a habit of falling into what I call local optima. And the reason you don't hear about it is you don't see all the blood, sweat, and tears that the researchers had to go through in order to get that paper published. You don't hear about, I had to tweak this reward function, I had to change the topology of this network, I had to do this, I had to do that. And now, ta-da, I have the result. So you spend a lot of time trying to figure out how to get out of this local optima. But if we want to actually deploy this in the real world and make it efficient and make it a technique that can be used in system engineering and real products, we need to be able to get past that local optima problem and struggle for 6 months to figure out how to do it. So the 3 challenges I claim that we need to overcome are the sample efficiency. And one technique people have used for that is they try to build models of the environment. But even with the best models, say robot arms, we have fantastic models. If you try to learn against that model, and then you try and apply it in the real world, it often doesn't work that well. In fact, I think Pushkar showed a video of that last week where you had to actually change the model and inject noise in order to get the model to actually simulate the real world very well. As I said, we also need to start thinking about how we get the actual model to be small enough to put onto edge devices. That's another challenge that we need to do. And then the final thing is we need more robust training techniques. So today we're going to look at an example which I think tackles these particular challenges. But before we even get there, I want to say that there are a lot of people working on this that actually have published interesting papers. We're just looking at one example. But those papers tend to have something I think is quite interesting in common. We're back to our reinforcement learning model here. And what you can see is we still have the agent at the top, but now we have two boxes in it. Now you might think this doesn't seem like a step forward. We had one box before, now we have two boxes. So what's been happening is people started to realize that they can try building a model of the environment, and I call these uncertain dynamic models. And these uncertain dynamic models try to learn the environment, but just what they need to know in order to solve the problem they're trying to solve. And they have an interesting characteristic, is that almost everyone that's experimenting with these understands that these models have a level of imprecision, like they're not completely sure about what the environment is, but they have some uncertainty, and they try and control and exploit that uncertainty. The second part is the policy network. And the policy network is the thing that actually says, what is the action I'm going to take? Now, the policy network can train as much as it wants against the uncertain dynamic models. So if you want to run a million simulations to try and figure out what the right policy is, you can do that, but you're not actually interacting with the real world right now. But whenever you interact with the real world, whenever you send an action down to the environment, you scoop all that information up and you feed it back into your uncertain dynamic model and try and make that model better and better, so that you can actually get to the result that you want. And I should mention, I also should mention that we're looking at one uncertain dynamic model today, but there are many different approaches that are getting taken out there. So there was one mentioned at the last talk, which is the MDNs. That's one model you can use. People have also been using Bayesian networks, probabilistic programming. And the model we're going to look at today for the uncertain dynamic model is actually something called a Gaussian process. Oops, I think I went the wrong way, sorry. So the algorithm we're looking at today is called plaque drops. It's in the paper that's up on the meetup invite. I'm actually not going to try and pronounce the author's names. I think I'm going to embarrass myself. But it's a good paper and it's really worth looking at. So for that uncertain dynamic model, they use Gaussian processes. And I'm going to give a backgrounder on that in case you guys aren't familiar with that. For the policy, they're just using a very simple neural net. I think in this particular paper, they're just using 10 neurons as one hidden layer. And then for the training, they're using a technique called CMAES. And I'll give a quick background on that, because it's kind of important to understand how the whole paper works. So if you're getting a bit rusty on that, or you haven't seen it before, hopefully you'll have enough information.
What does CMAES stand for?
Covariance matrix adaptation evolutionary strategies. Okay. A bit quiz after me. It's a very clever technique, and it's a classic technique by now. I mean, it came out, I think, in the mid-2000s. Is that right, Pushkar?
A little bit later than that, yeah.
So let's look at a Gaussian process. So this is an actual Gaussian process. And what I did was I fed XY data points into it. And the XY data points I fed into it are represented by the little circles you see up on the screen. What the Gaussian process then does is it tries to be able to predict what's actually happening in this space. So if I ask it, what do you think the value at 8 is, it will come up, and this red line represents what its best guess is, given the data that it has right now, for what the value at 8 is going to be. The blue arrow is the uncertainty. So this is actually an introspective model. It understands that it doesn't necessarily understand things terribly well. So when you're near data points, especially if you've got a couple of them clustered together, it's pretty certain you don't see much blue. But as you move away from where it's ever seen any data before, it gets less and less certain as what the answer is. And that actually gets exploited in a lot of these algorithms that we're looking at to help it actually learn more about that environment. The Gaussian processes have some really nice pros. It's very easy to build a Gaussian process model. You basically take your XY pairs and you just shove it into it. So that's really nice, it's simple. It understands this uncertainty, and that really helps if you're trying to explore or exploit. Do I really know enough to rule out this particular path? No, maybe not. It could be a lot better than I think. Let me try going down it. You'll get more data, and maybe the UDM doesn't look so attractive then, but at least you've discovered that wasn't an attractive way to go. As I mentioned, they're predictive, so that means that if you're trying to simulate against it, even if you don't have any data in that part of the universe, at least you've got some guesses. They might be great guesses, but you also know they're not great guesses, but at least you have some sense of what's happening there. And you need to make some assumptions about how that model fits together, which we call kernels. And what's nice with Gaussian processes is you can actually use your own kernels, you can use standard kernels, and you can mix and match kernels. So you can get kernels that are very good at looking at, say, periodic data. So if you've got a data set that has a lot of periodicity, say on an annual basis or a weekly basis, you can use a kernel like that. And then you mix it with the standard kernel, which says data points that are clustered close together, give us some real confidence as to what's happening. But if we're a long way from a data point that we've never seen before, then we get a lot less confident as to what the actual answer is going to be. There's some cons to them as well, unfortunately. Nothing's ever free, it seems like. The first one is, once you get past 10,000 XY pairs, it gets pretty unwieldy to build Gaussian processes. There's some tricks and techniques with Gaussian processes that allow you to extend that maybe to 100 or even 1 million data points, but the stock ones that you're going to find in, say, Python or MATLAB are only going to really give you good results at about 10,000 points. It also takes time to predict the values. So that means when you give it an X and say, what's the Y, it's not that fast an operation. So when you're doing simulations, you need compute power. The good news is it's very parallelizable. So if you've got enough compute power, you can do a lot of simulations with it. And then the final thing is it doesn't expand to high-dimensional space well. So what I mean by that is if you have some kind of a control problem with 100 different variables coming into it, the Gaussian processes are not going to give you a very good model of the space that you're trying to understand around that. However, in the real world, most of the time we're dealing with problems that are not that high dimensional. So how does blackdrops use Gaussian processes? Well, so what they do is they take the state and the action space and they map that into the change in the state. Blackdrops is the name of the algorithm that we're just in the paper. They call it blackdrops. So what I mean by that is if you look at the current state and you apply the current action to it, they map that in the Gaussian process to the next state, st plus 1, minus the current state, also the change in state. So that's one case where they're building up this Gaussian process. If you know where you are, you say, I want to take this action, then it tries to predict then what would be the change of the state in that reinforcement learning cycle. And the other one that they do is they take the current state and they map it into the reward for that particular state. So they throw up two sets of Gaussian processes. So in this particular implementation, they use one Gaussian process for each dimension in S. So imagine that you wanted to figure out where the end effector was in a robot arm. Then what would happen is they would use three Gaussian processes. They would look at the X, Y, Z, the arm's act, what the action is you apply to the arm, and then what the delta X is. They'd use another one for the delta Y, and they'd use a third one for the delta Z. Now, a logical question to ask is, why do they map the state space and the action to the change in the state? Why not just map it to the new state? So instead of doing this st plus 1 minus st, why not just go to st plus 1? Because Gaussian processes should be able to map that very well. And I don't have a very good answer, unfortunately, for that question, other than to say that it doesn't work well. So I can tell you it doesn't work well trying to go to the state. And it's not just blackdrops that's having this problem. This problem also happens in pill code. It also happens with other people trying to use this in predictive ways in neural networks. But going to the changing state is actually much better than trying to map to the new state. So if anyone knows the answer to that question, Do you know the answer? All right.
So in quantitative finance, you all the time don't deal with the raw value, but rather the change. And the reason is because the random number N01, you can add those, and basically you can kind of like these changes are more normally distributed, perhaps with some factors rather than like dealing with the raw values. So almost all the time you must first take the first differences of the series and then work with it. So essentially that's what we're doing here.
Okay, so you have one explanation.
So it's mathematically more tractable to deal with normal variates, and it's only achievable if you first difference.
Okay.
Yeah, is that domain dependent, do you think, or is that just, have they run that in simulations and in all different places, or is
It's a common problem. I mean, like I said, it could be that is the reason, but I haven't actually seen anyone give a reason. I've seen people say also in research papers it didn't work well trying to map to the state, and they found that the delta was better. But no one's really provided much of an explanation theoretically for why a robot arm would be like that. Yeah?
I don't know, but I can perhaps guess where you might take a sampling of different state action pairs and look at the delta and look at the distribution that follows and make some inferencing potentially based on that, which you would not do if you just had the subsequent state. Maybe.
Yeah, and I think that's close to the argument that you're making as well, that the distribution is nicer of the deltas than it is of the actual states. And that could be what it is. So the other thing, if you read the paper through that was up on the website, you might go, why do they even use the Gaussian process for the reward function? And they don't need it. They can always calculate the reward by what the implied state is in all the examples that they give. And there are two reasons for that. The first one is it's actually rather nice that it works, because I'm going to hopefully have time to give some examples of how you can exploit that in the real world. But the second one is I'm going to show an example of a later paper from the same group where they do exploit that particular fact. So it's still the black dot algorithm they're using, but they're now exploiting the fact, along with a couple of other things, that the Gaussian process for the reward function now works for. The other thing is I'm not sure in this particular paper that mapping directly from the state to the reward function is optimal. So if we have time, I'll give you some thoughts on other ways you might be able to do that mapping and actually get more results out of the system. So that's hopefully everything you need to know about Gaussian processes. So we're going to be seeing them again in a few minutes in the algorithm. The other thing I want to do is do a quick CNA ES review. So over here we have a very friendly function. This one, you always assign in first semester calculus class, and you say, use your Newtonian methods to find the global optimum, right? So it's not an easy thing to try and find that global optimum using conventional techniques. And a bunch of things have come around. One of the later techniques, which has really been adopted heavily, is called CNA-ES, and it can find good optimums of these kind of functions. So it is an optimizer. It's completely black box. It doesn't really care about what the underlying thing is. It's just like, give me your parameters, I'll tweak it, and tell me what the answer is. And it works from that to actually figure out where the optimums are on functions. It's been shown to be very robust against noise in the data. It's good when you have non-differentiable points, and it's even pretty good if you've got discontinuities, depending on how many discontinuities. But a few discontinuities really does not affect it particularly. So on the screen now, this is basically pretty much like the same function you just saw on the previous page, and you actually see the algorithm in working on that. So what happens is it starts here near the middle, and it chooses just a bunch of random points for the distribution around the point you say start here. And what it does then is it looks at the best of those points, which are the green dots. Hard to see, especially for colorblind like me, but if you can see the green dots, those are the best ones out of the initial random sample that it chose. And then from those best ones, it calculates a new distribution and then chooses a bunch of blue dots, which are the offspring, and it then looks at what were the best of those blue dots. And you can see when it starts over here, it's quite tightly clustered, and it very quickly explodes, and it even figures out what's the right way to explode. It's moving up towards that global optimum. And so this technique can be used, as I said, for pretty much anything with a reasonable number of dimensions. So if you've got anything probably up to about 1,000 to 5,000 parameters, this technique's proven to be very robust and useful for actually solving those kind of problems. Once you start getting more parameters than that, it's gonna start falling down.
What is the difference between this and PCA, primary component analysis, in your
Well,
view?
so the principal component analysis is really trying to separate information by looking at what the greatest variance is. This is really just trying to find an optimum in your data set. So if you think about, you've got some magic black box and you're saying, what's the most I could ever get out of this magic black box? You know, say the most power or the most efficiency. And I've got these 20 levers I can move. This guy will actually figure out what's the right setting of those levers to try and get the optimum power or the optimum efficiency, whatever you're going for. PCA allows you to try and separate things into different groups. And it does that through a technique where it breaks things into the maximum variance and the next maximum variance on the different variables.
Question?
Yeah.
So does it sample the space and it's trying to figure out the optimum that way, or is it trying to use information on the gradient at all?
It actually really just uses, it doesn't really use the gradient in the sense that you might think it uses the gradient. What it does is it looks at the distribution of the best points at every iteration in the evolutionary strategy. And as it does that, it starts saying, in this particular case, when it starts off over here, it says, oh, you know, when I'm starting looking around at the points, you know, I think I need to go further greenfield. I need to go further afield to find better points. And as it spreads out, and it spreads out more and more and more, it starts realizing that the best points are actually now getting closer and closer together, and then you get that kind of convergence on the optimum. There's a lot of good websites, by the way, about CMA, yes. Yeah.
So is it using like a Gaussian distribution to determine the sample points?
It does. So it's sort of an n-dimensional, so depending on the number of variables you have, yeah, so it's an n-dimensional Gaussian distribution that it uses. So it's looking at the covariance, that's why it's called the covariance matrix adaptation. So it's adapting the covariance matrix.
And then it uses like a reward function to determine the...
Yeah, you need to give it, when it feeds in the parameter, you need to tell it, well, how well did that particular set of parameters work, yeah.
So what's the difference? Do you know a cross entropy maximization?
So what's the difference between?
Do you know cross entropy, the TEM cross entropy maximization?
That's a good question. I'm not sure I'm qualified to give an answer to that one.
Okay.
But we can talk about it more after the meeting. But it's as a technique, this one you typically think of it applying it to something that's static, where you're just controlling the variables on it. But we can talk about that more afterwards.
So pretty much this is like the simple Gaussian kind of model, right? If this were not applied in a reinforcement learning space and simply like the Gaussian approach.
Yeah, this actually could be applied to lots of different applications. It's not just reinforcement learning. This particular paper uses it for the training in reinforcement learning, we'll see. But yeah, it's got wide-scale application. You can use this in lots of different places.
Is there any rule of thumb about how many different samples you take based on how many parameters you're optimizing?
There is some sort of rules of thumb, but the best thing to do, and you want to make sure you're getting enough coverage for your parameters, right? And so you typically think of scaling it up as something that grows with the number of parameters and the number of data points that you need. But the best thing to do is usually kind of play around, and you'll see if you're getting good convergence pretty quickly as a rule for your particular system.
How computationally efficient is it?
Okay, so actually, it's not too bad, but it's
A little
let's
more
just say
expensive
that
than...
I'm not stuck in NVIDIA if you guys are all sold on CMAES.
Cool.
Okay, so let's get back to backdrops, because that was just kind of the background so you can hopefully understand the algorithm. So with backdrops, what we have, we're back to our agent, and it's operating on its environment through actions. And we now have our certain dynamic model, which we're building out of Gaussian processes. We will see we're using quite a few Gaussian processes inside it. Our policy is just a very simple neural network. And now we've got our training technique, and we're going to train the neural network, not using backpropagation or the other techniques you might have seen before. We're actually going to train it through using CMAES. So when you go through the paper, you will find that they have this nice diagram of the algorithm. And I want to kind of break it down for you so you can understand the different parts of it when you're going through the paper. So this is the first half of the algorithm. And all they're doing in the first half of this algorithm is they're doing some random moves with whatever it is that you're trying to control. They just start off at some location and they give it some random actions and they just record what happened in the environment. So you can see here on line 9, what they're doing is that's where they're taking the state space and coupled with the action and they're mapping it to the change of state. This notation I'm not wild about, by the way. If you see this tilde, this tilde over the x, that's actually the state crossed with the action. Not sure why they did that because it sort of implies it's more like the state. And then on line 10, they're just updating their database of the reward. So, we got to this particular state, what was the reward we got for this particular state? So that's all this is doing. They typically, by the way, they just do this once in each of the examples. They just run one random action, one set of random actions at the beginning, and that's all they do, and then the algorithm actually kicks in at that particular point in time. So then the second half of the algorithm is really where the magic happens. So the blue box shows you that they're building up the Gaussian processes for the state cross action to the change of state. And as I mentioned, they build up one Gaussian process for each dimension of the state. So if you had a 4-dimensional state, they'll build 4 Gaussian processes. They all have the same inputs. They all take the same state cross action, but they just look at the delta of the state variable for the 4 dimensions. Then they also train the Gaussian process. They have one Gaussian process that's trained on the reward, so they just take the state, multi-bit dimensional again, and map it to the scalar reward. So hopefully that's reasonably clear, seeing Gaussian processes, and hopefully that works out pretty well. The next line is where they train the policy. Based on the Gaussian processes that they have developed, they train their policy using the CMA-ES. I'm going to spend a few slides on this because it's rather abrupt in the paper when they get to that point. They just kind of leap into it. They don't really explain the motivation very well. So we're going to go through that right after this slide in a bit more detail. Once they have their policy trained, so their little simple neural network, they then try rolling it out. So this green area is actually when they're now interacting with whatever the robot or the control system, whatever they're trying to do, that's the green area, and it has nothing to do with the Gaussian processes, it has nothing to do with CMA-ES, it's completely independent. They just take that simple neural network and they try it out and see where they end up. Once they've done that, they go, okay, we've got some more data now. And they can take that real world data, so the D, which is the state action space to the change in state, and the reward function, which is the state to the reward, and they feed it back into their Gaussian processes, so they can update the Gaussian processes and they start the whole process off again. Yeah.
How does the initial Gaussian model get, what data is feeding the initial?
It's this first part where they actually just run some random actions. So they just start off with some random actions and get some data, and that's what feeds the initial one. Okay, so let's look at how that training, that yellow line. So it's one line, but it's quite a few slides. So the way it works is this, is they select a bunch of random weights for their neural network. And so now you've got a neural network. It's just initialized with random weights. How you usually start off with any kind of a neural network. You'd start off with some random initialization of the weights. They start off at S0 and then they roll out the policy. So they take that neural network, they apply it to S0, it gives them, this is the action, A0. From A0, from the Gaussian process, they can calculate what the change in state, what that estimate of the change of state is going to be. So they take S0 and A0, that gives them the change of state, they add it to S0, and you get S1. Then you do it again. You take the neural network that you have, you apply it to S1, it gives you the next action. From that next action and the next state, you can use the Gaussian process to try and guess what the next state is going to be, and you roll it out. At the same time, you also calculate out the rewards. So for each state you think you're ending up in, from the above line, you calculate out what your reward is. Then, you do that again. Lots. So you select more random weights. You start off at S0, you roll out that policy for that neural network. You collect the rewards for that neural network, and you keep repeating it. And this is like building out that initial bunch of blue dots that you saw in the CMAES video. That's what you're doing, is you're building out your, just basically random things for the CMAES to start using. Once you do that, you go, what are the top rewards that we saw? And I put top in quotes because it's slightly more complicated than that, but we'll get to that later if we have time. But what they do is they say, well, you know, what were the best 10% of our random policies? Probably most of them were crap, but some of them are going to be better than others. And so you then update your mean and your covariance matrix based on what the top ones are. And then what you do is you use that to sample another set of random weights. Let's say you start off with 300, you took the top 30, you updated your mean and covariance matrix, and then what you do is you select another 270 sets of random weights based on that mean and covariance matrix, and you try it out again. And that's when you saw the dots starting to expand out, right? And so you do that. In this case, in the paper, I think they typically do it 5,000 times, and then they hope they end up with a good global optimum. The best policy, they end up after going through that, select the top, throw away the rest, get some new ones based on the distribution of the top, rinse and repeat 5,000 times, and hopefully you've got a pretty good neural network at the end of it. So questions about that?
Yeah, that covariance matrix, that's a fresh one every iteration? So you throw away the old one and just get a new one?
Yeah, I think they throw it away each time, yeah.
Okay.
Yeah.
So, the reason for, I'm just trying to understand the reason for using CMAES to train the neural net. Because the neural net still has the ReLU or the nicely differentiable non-linearities. Am I right?
That's right.
So why go try something very complicated and not use the gradient descent or something?
So the problem really comes back to the reward, right? So what you don't have here is the ability to necessarily know what the real reward is. You're actually hunting for it in a potentially much more complicated space. So your reward function is not nice and smooth and differentiable and continuous. You know actually very little about it. And what you're trying to do is get the right weights to give you a good reward. And that's where CMAES really excels. If you had a situation, in fact, I'm going to show you one algorithm where you can use something much closer to what you just described. If you have a nice, well-understood reward function that is going to be smooth and continuous with respect to the weights of your neural network, you could do that, and you really understood that reward function well. But in this case, you don't really understand what the reward function is. You have to hunt around to try and find the weights that are going to give you that good reward.
So what kind of application you are talking about?
So I will look at some very specific examples, actually. So I'm going to show some very specific examples where it would be hard to do that with conventional techniques.
This might be off the wall, but it seems like a variant of selective breeding.
Yeah, it's kind of like it's an evolutionary strategy, right?
Yeah.
So it seems like this would work well if the next state only depends on your action. Like if the environment is not stochastic or something, because you're trying to predict the next state.
Right.
It seems like it would kind of fall apart if like things are happening, like it depends on like percentages or something.
Yeah, but that's definitely criticism with the technique. I'm going to show one example also a little bit later on where you can actually see it's quite robust against that as well. It's surprising, but it also gets back to that reward function. Is the reward mapping that they're doing between just the current state and the reward really the right model? And I'm not sure that it is the perfect model. It works for some applications, but I think you could do better than that and handle some of the situations you're talking about as well.
In the previous slide,
Yeah.
the start state is the same for all the network, or?
Yeah, they all start, in this particular paper, they all start at the same initial starting state.
So my best network is biased to the start state.
Yes, in this particular case.
Why we are not make that starting state again at random, because we want a network that works for all the start states. We don't know that where we are at the beginning.
So you want the truthful answer? Or so they're trying to publish papers, right? And they want to show that this can converge as quickly as they can. And this is what the competitors are doing as well in their papers. So people are kind of rigging their papers for the fastest convergence. Is really the simple answer. But yeah, you could, and it would be more useful to demonstrate that your algorithm's working better from all kinds of different starting states. So I think that's probably the most truthful answer. Because I'm not the publisher of the article, so I can, Yes, sorry.
One other small question, is calculating the reward, is discounting relevant in this scenario at all, or completely irrelevant?
In this particular case, what they do is they choose the reward based on actually trying to maximize the reward across each one of the time steps. So you're selling together in this particular case. There could be some advantages to doing that, I agree. And once again, that also gets back a little bit to, is the reward function, the way they're mapping it straight from state to the reward, the optimal thing? And I'm not sure that it is. Okay, so hopefully at the end of this, you found a good reward function. And so now you're ready to try that policy out. You can roll it out. And when you do that the first time, it is probably going to be a horrible, unmitigated disaster. But you'll have learned a lot. You'll have learned a lot more about the space. You'll have learned a lot more about how actions are affecting the state. You'll have learned a lot more about the reward function. So you now feed that back into the Gaussian processes, and you try it again. So you might go, well, how well can this really work? I mean, it seems complicated. It seems kind of goofy in a lot of ways, the way they're going about this. So I want to show you 3 examples. The first one is actually a technique that's been around for a bit called pill code. And it's got a number of limitations about reward functions, but it's using analytical solutions. You can train things much more nicely, that kind of thing. And it has to try getting a pendulum standing straight up. All it knows is it's got a control that happens to drive a motor, so it can drive a motor, but doesn't know anything about how it drives the motor. And it knows it needs to try and get the encoder on the pendulum so it stays up. That's all it knows, and it's got to learn that. So we'll look at that video. We're then going to look at black drops, and it's controlling a cheap, inexpensive, rickety, wobbly robot arm. It's going to try and figure out how to touch the blue target. And then I'm going to show another version of black drops that's slightly more sophisticated, where they took the hex robot, they ripped off one of its legs, and it had to try and figure out how to walk as fast as it could in a straight line. So hopefully this works. We'll find out. Okay, so here's pill code. And remember, it has no knowledge. It is starting off, it's building up that gap. Pill code also, by the way, uses Gaussian processes. It's building up its Gaussian process. So this was its first run. I moved my mouse a little bit better. And it was just random. So it just did its random actions. So now it's off doing its random actions again. So it ran two sets of random actions. So now it's actually going to try doing something. It's going to try saying, okay, can I get this thing to stand up given the information that I have? The answer was not so well. That was the first time you try it, usually a disaster. But now it's going to try it for the 4th time. So it's now developing talents that are maybe useful in other industries, but it did actually get to go around at least. So it's starting to get closer now, starting to figure out that space that it needs to really get the control of the system. So now it's starting to get close. It's really starting to figure things out. So as it gets closer, you tend to get very fast convergence now. So once it starts getting in the ballpark, convergence tends to get quite a bit better on these things.
Oh, wow.
And now in the final run, they just let it run. They don't stop it. And you can see that it will have developed. Well, maybe you would see what would happen.
Do you know how much compute they're running behind the scenes there to get it? That's fine, let's look at this.
Okay, so the next one.
We know what.
Okay,
You know why they use that center?
yeah, because it's actually supposed to try and stay in the center as well. It's a little bit harder, even than the problem I described, so it's supposed to try and balance the mode out. So here's Black Drop's running, and it's doing its random motion on its little robot here. So that was his first attempt, and it just basically went off and just tried something random. So it runs again, trying to get to the target. As you can see, it actually got a little bit closer that time, so it's starting to get convergence and actually trying to get to the target as it goes through this process. And now it's sort of there, no, off in left field. But it's, every time it does one of these things, it really gets a lot more information about its space. And it will, as I said, quick to start getting there. It's almost there now. It's kind of, yeah, almost got to it. So it's starting to learn how to actually interact with its environment. And then finally, I think on this particular run, it actually gets to its target. And so, yes?
What information is it being given to know how close you got to the target?
In this case, they're using, I think, a 3D camera, and they actually use that to tell it where the end effector is in relationship to the target, and that's where the information is getting. So then I want to show you one more. This is a slightly more sophisticated version of Black Drops. It is basically using exactly the same algorithm, but they've made some tweaks to it to improve the performance. And in this particular case, they're abusing robots. I hope there's no kind of organization, prevention of cruelty against robots that are watching this. And they pull off one of its back legs and tell it, okay, now you need to try and walk as fast as you can down this straight line. So the first attempt's pretty pathetic. So you can see it now hobbling away. And now its third attempt, it's actually starting to make some real progress on its third attempt. Fourth attempt goes a bit off track, and now it's really starting to kind of get the hang of this. And as you can see, the speed actually goes up. So it's now getting up to pretty good walking speed at this point in time now. And managing to track down that white line, and then they give you the nice run of it actually walking down the white line. And so this ability for them to relearn their environment very, very quickly is what makes, I think, these algorithms quite exciting. This starts opening up the possibility to really introduce this stuff into the real world and actually start solving some interesting problems with it. And I will put the slides up so you guys can actually look at the videos after the fact. So we've actually tried replicating it, and what we did, we started with actually just using a 2-degree freedom arm. And it's a real-world arm. It's an inexpensive Dynaphixel, use some Dynaphixel things and a cheap robot arm. And we started down here, and we said, this is your start at the top here. You have to kind of swing up like this. Try figuring out how to do that just using 10 neurons. And this was pretty typical of what we found. It was quite stable. It worked quite quickly. And running through here, it would typically just take 5 iterations for it to actually home in on that particular point. We also tried it for a 3-dimensional space. We found it was a little less stable. Initial conditions were important. We'll talk about that in a minute. But it also was working. And then, unfortunately, the programmer had to run back to Russia because his phone was being diagnosed with a nasty disease. So I don't have a demo to show you today, but next time, I hope I can bring a demo of it actually working. There was a question about compute power. How much compute power does it take to do this? If you want to get optimal results for the shortest number of runs, you're going to be on, say, a 32-core system. It's going to probably take you 10 minutes to update 3 cycles for something like this, just to kind of put it in perspective. Yes?
The examples are episodic tasks. Does this still work for continuous?
Yeah, you can definitely train the source to work on continuous tests. You'll see a lot of results in the paper, and I just want to go through them because there's an interesting thing here with the exploitation and exploration. So in the paper, first of all, if you're writing academic papers, please consider colorblind people like me before you start using these kind of telescopes. Because it makes it almost impossible to read. But They compare themselves to Pilco, which is one of the first kind of techniques like this out there, and they consistently do very well against Pilco, and they're much more general purpose, which is what makes this kind of an exciting technique over Pilco. But the second thing to note is they compare themselves with a neural network versus a Gaussian process, and as a rule, the simple neural network actually outperformed the Gaussian process as the policy function. So you don't need to use a neural network as the policy, and we'll talk about that if we have time, other things you could use there. But the Gaussian process didn't quite perform as well typically as a neural network. And then they also look at what they call the black drops in the nova. And this is a very subtle but interesting distinction. So in the black drops case, what they do is when they do that rollout, and they look at the action of the state, and they go, where am I going? They don't choose the mean value for the state. What they actually choose is a value based on the distribution of what the Gaussian process thinks the value is going to be. And when they do that, they consistently do better than the nova, which is when they only select the mean value from that Gaussian process. So when they put in the state and the action, they just say, what does the Gaussian process say the mean value is? And when they choose that, it does not do as well, or it's consistent across a bunch of tests where it doesn't actually do as well as selecting data points that come from the distribution of the output. And I believe the reason for that is it's really helping with their exploration. So when they're uncertain, and you don't really know what's happening in that space, you may try going there then at that point in time, and that actually seems to be leading to faster and better convergence. I think their results are achieving very good results in comparison to Pilco. As I said, they're much more general purpose, and as I hope to have demonstrated, they are actually very fast at learning, and that makes them, I think, very exciting to start applying to applications. This one is that top comment I made. So there's a situation where the ranking of the best neural networks, the best policies, the difference between the ranking may actually just be less than sample noise. So if you just resample that policy, remember they're choosing, in some sense, random points when they come out. And you might find that that distribution of rewards is smaller, but if you just rerun it, you might get rather different reward. When that happens, and they do tests for that, where I call the noise of the sample is greater than the difference in the ranking, they deliberately expand the covariance matrix. So they look, once again, that's helping with the exploration. They're looking further afield. They're trying to find more interesting data points. Some observations about black drops, since we've been using it, it is sensitive to initial conditions. Now, this is a criticism that is not just true of black drops. It's kind of one of the dirty secrets of reinforcement learning. It tends to be sensitive to initial conditions. And in the real world, that's actually less important, because what we're trying to do is train the policy as a rule. So we don't care if it takes a few tries before we get a good policy, because that's the policy we're going to deploy on the actual device. The other thing is the compute power versus the learning speed is not really optimized. So it takes a big compute power to actually calculate the next update. And they're doing that because to get bragging rights, you've got to say, I did this in 5 tries, where you took 6. Where in reality, you might use a lot less compute power, but you could do it in 10 tries. So that's something to bear in mind if you're playing with the code. The other thing that's kind of a shame is time is not really fully implemented at the low level inside the code. So the C++ code is available. You can go get it from the Blackdrop site. And time is not fully implemented at the low level, which is a shame because it would open up some more applications. I don't think it's that hard to add, it's just not currently in there. And the final thing is if you want to experiment with the code, it's got heavy memory requirements when you're compiling it. So I recommend 128 gigabyte systems when you're doing the compilation. You can get away getting sort of a bare minimum system working with 16 gigabytes, but bear that in mind is it's not very efficient when you're trying to do compilation of the code. So hopefully now I'm starting to convince you guys that this is something you can really start deploying, because if you have your policy, you can put that on a relatively small module. I mean, the policies in this case, these 10 neural networks, you put on a tiny microcontroller, you know, Cortex M4 or something of that kind of class would have no problem running these kind of policies. And then you can put your uncertain dynamic model and your training up in the cloud. And at that particular stage, you can actually be gathering data from end-user devices, and you can feed it back to the cloud, and you can retrain better policies. You can check that those policies are really working well before you push them out and deploy them at the edge of the network. I think a bunch of new applications this can enable. The first thing to note is that CNA-ES policy will allow you to start training things that have dead bands, hysteresis, You could even imagine using it to linearize PID controllers. So you could, as I mentioned previously, the policy doesn't need to be a neural network. CMAES just doesn't care what it is. So if you took a PID controller with, say, 3 parameters, and you said, that's my policy, CMAES would still tune it perfectly fine. In fact, it'll probably do a better job than you could do. And you can start imagining adding linearization to your PID. You can start imagining doing things that you would never do if you were rational, like doing double integrals or double derivatives. So your PID controllers, the CMAES policy will still tune it really well. I like to always say that no one ever left tuning a PID saying, gosh, I got everything out of that system. I know one of the laughs I know is trying to tune a PID before. The other thing is you can start allowing the system to compensate for errors. Remember that reward function is actually a Gaussian process? So you can imagine having an end effector with some kind of a proximity sensor, and as it gets close to the target, really the relative error is all that counts. It will adapt, even if your robot arm is not that good, a bit wobbly, things are not quite aligned correctly, it will adapt very nicely to those kind of processes. You can also now optimize for hard-to-model features. So I think with a little bit of change to the reward function, the way you do it, you can imagine putting an accelerometer onto your robot arm, and now you could optimize for the smoothness of motion, which is important if you're trying to move things like liquids. You don't want a lot of jerk, you don't want a lot of vibration. You can now have the system tuned for that, and that's really difficult to simulate and get out of real-world systems when you're doing that, even with conventional control techniques. You can see that there's some nice things with self-healing systems, and they already got an example of that, but you can imagine that also happening out in the real world. As your systems age that you've deployed, if you've got a medical device, let's say a scientific device with robotics and that kind of stuff that has 10, 15-year lifespan, you can now actually roll out new policies if a device is starting to have trouble, alignment isn't quite as good as when it was new. You can now actually have these things adapt without necessarily having to roll a truck to go fix them. You can also imagine customizing things on a unit-by-unit basis. So if you look at battery management systems, they typically take stacks of cells. You take your cells, you put them together in a stack, then you start building up stacks, and then you start building up stacks of stacks. The trouble is a lot of characteristics about an individual stack is governed by the weakest battery in the stack. And so you get a lot of variation even between the stacks. You can now imagine this system starting to learn the individual behaviors of each stack, where they're weak, where they're strong. You can optimize better for coulometric efficiency. You can estimate state of charge better. There's a bunch of stuff that you can start using this technology for in that particular space. And then the final one that's kind of a pet peeve of mine is I have a client that I work for, and I swear whoever designed the HVAC system is just trying to thermal cycle the humans. I mean, you're just like, they're boiling hot one minute, and the next minute you're freezing cold. So you can imagine a system like this where you've got your cell phone, you say it's too hot, it's too cold, too hot, and you can start learning how to actually control the HVAC system. That'd be great if we could get back to work in the 21st century. Quick note on the reward function. I made some comments on this. I want to keep some time here to get into questions, but I don't think the reward function is optimal. We're certainly playing around with that. We think that we can do some more interesting things with the reward function than what we have right now, just going from the state to the reward. So something to bear in mind if you're actually playing around and you're trying to get some other characteristics working, but that would be a natural point to start playing with. And, just kind of want to wrap up that this is an actual technology, and it's just one example of many technologies coming out in reinforcement learning that I think start really giving us the ability to deploy this on real-world systems. Is it going to be as dramatic as AlphaZero winning the world champion at chess? No, but it could make your life a lot easier if you've got a difficult control problem and you're struggling with the standard control optimization techniques you learned all those years ago. Because they don't really consider hysteresis, they don't consider dead time. They don't consider adaptation that well. These kind of techniques, I think, now are really getting ready for prime time. So, if you have any ideas, you want to talk to me, bounce questions off me about ideas or questions about the technique or that kind of stuff, please reach out, call me, email me. I'd love to talk about ideas. I'll be happy to take any questions you guys have right now.
You mentioned possibly keeping track of historical information. Would it be overkill to use an LSTM, or could you get some traction out of that?
Possibly. I mean, I think there's lots of possibilities of stuff you can do there. I mean, these techniques are new, right? So everyone's experimenting and trying to figure out how to use them.
Have you tried that yet, or?
No, we haven't tried that with this particular one. I mean, we definitely look at changes in Gaussian processes as kind of an interesting, if you imagine you take a Gaussian process at one point in time, a pretty good model of what the state space is, and then you take another Gaussian process at a later point and sort of compare what's happening between them. That actually kind of gives you some interesting information about what's happening to your system, how is it aging, how is it changing.
Yeah, there was just one thing I didn't quite catch in the talk. In the paper they said there's something about they were able to capture the uncertainty from the Gaussian process model and account for that. I was wondering if you could go over that again. I think that seems to be the major innovation that they had, or at least they were claiming that. So is that like the variance?
Yeah, I went right back to the slide. So here, this is one example of where they're capturing that. This is the difference between the black drops and the Nova. So in the Nova case, they were just using the expected mean function from the Gaussian process. And this probably wasn't the best chart to choose. There were some better ones that showed that it really was performing somewhat worse than the black drops algorithm, where in that particular case, they used that uncertainty, and used that uncertainty to actually select what the state was going to be by choosing it from the distribution from the Gaussian process.
So did they like sample a few times, or did they just pass the variances to the neural controller, or?
So that gets actually to this slide. What they do is that they do resample some of those policy rollouts. They just resample a fraction of them. And they look to see how much the reward moved when they did that resampling. And if the reward moved by too much, then they would expand the covariance matrix while looking for the optimum.
So they were looking at variance in the covariance matrix.
They were actually looking at how much the change in, if you did another rollout, how much did it change the reward function versus the difference in the actual rewards that they had.
Okay.
And they just expanded the covariance matrix by, I think, a set amount, like maybe 10%. They just kind of boosted it with a scale value.
Gotcha. And that's what they just kept iteratively doing that.
They just kept iteratively doing that each iteration if they were still seeing a lot of noise in that rankings, basically. The rankings could switch.
Cool. Thanks for going through that. That's helpful.
Yes.
Yes, in the previous slide it said that the neural network was better than black drops of G2.
So the neural network, they use a neural network as one policy, and then they use the Gaussian process as another policy. As I mentioned, you could also use a PID control as a policy. So that their code is actually set up, I think they've got 3 or 4 policies actually in the code that you can experiment with. But the ones that were the best were the Gaussian process and the neural network. But they found the neural network outperformed typically the Gaussian process either. And one of the things I didn't show today that's actually kind of interesting, Bosch did some work using the Pilco algorithm where they tried to do throttle control using Pilco versus the standard way they do it using PID controllers. And they found that with Pilco, they could train that to easily outperform very quickly their best training on throttle controllers. And Bosch knows something about throttle controllers. So the fact that they could get that to work a lot better very quickly, I think is pretty encouraging for real world applications. Other questions? I'm happy to talk to any of you guys after the meeting, by the way, as well. So, all right. Well, thank you for listening. I hope you'll
let's thank our speaker Oliver again. And there are some waters and snacks or cookies back there, so you can grab it. And we have the space until 8:30, so yeah.